All right, so I think the first page we had was page 2 from the topic 8 packet. Let me give you my answers, and I'll give you what percent of people got those questions right, and then you can let me know if we need to talk about them. So on page 2, number 28, my answer was C, and only 39% of people got that right. Does anybody want to talk about 28? I got one yes. So I'm only going to do it in pretty abbreviated fashion. So this is wave power, right? Wave power is governed by the power per unit length is 1/2 the wave amplitude squared times the water density times gravity times the wave speed. So we are doubling the amplitude and doubling the wave speed. But the amplitude is squared, so that doubling has to get squared. So in our power per unit length, we get a 4-time increase from doubling the amplitude, and then a 2-time increase by doubling the speed. So overall, we get an 8-time increase, or 8 times increase in the power. Other issues with 28? All right, 29, my answer was C, and 64% of people got that right. Anybody want to talk about 29? Not a single person. All right, page 4. We had all 3 of these. So number 26, I had answer A, and 62% of people got that right. Would anybody like to talk more about 26? Yeah? Okay. So in 26, this was kind of one of our energy density and fuel consumption calculations. So we want an expression that will give us how powerful this plant is in megawatts. So this is almost like a backwards calculation from what we did back 3 or 4 or 6 weeks ago. So what do we know? We know the efficiency of the plant is 25%. We know the energy density is 30 megajoules per kilogram. And we know that the fuel is consumed at 50 kilograms per second. So the first thing that I'd like to do is figure out what would the power be if I was 100% efficient, right? So that's going to be based on the energy density and the fuel consumption, right? Power, megawatts, is the same thing as megajoules per second, right? So I need to deal with these two values so that I get my megajoules, so that I'm getting megajoules per second for my answer. So what I would need to do is actually multiply the two things. So 30 megajoules per kilogram multiplied by 50 kilograms per second would tell me how many megajoules per second of electricity are produced each second. No, not each second. How many megajoules per second of electricity are produced, period. So that's 30 times 50. But we are only 25% efficient. So I know we didn't have to do it, but what is that? 1,500, I think, right? So 1,500 megawatts if we were 100% efficient. We are not 100% efficient. Now remember, this value comes from the energy density of the fuel and the rate at which the fuel is combusted, right? So we are not 100% efficient, we're only 25% efficient. So we're actually going to only be able to use 25% of that to make electricity. So let's look at our answers. Answers C and D are pretty bad because they're dividing 30 by 50, and we don't do that. If we divide 30 by 50, we would have units of seconds per megajoule. That's not what we want. So it's either A or B, and it's got to be choice A because choice A has us multiplying by 25 over 100, which is the efficiency. If we multiply by 100 over 25, that means that we're kind of like getting 4 times more electricity than energy actually stored in the food. Can't happen. Other issues with 26. 27, I got answer C. This was identical to the one on page 2.
Yeah. Well, the wording was different, but the question itself was
right. So I got C, and then the success rate on that was 36%, and which is actually very consistent with the other one. The other one was 39%. So I'm not going to talk about that one. We already did. 28, I got answer D. And the success rate was 54% on that. Would anybody like to talk about 28? Okay. So this is one of our solar power, how much much leaves the sun, how much enters the earth kind of questions, and I do think these ones are a little tough. Probably just because I'm slightly like geometry challenged. So we're told that we have a total amount of power radiated by the sun of P. Okay, so the total power going off in every direction from the sun. We are told that the earth is a distance d away from the sun. We're also told that the albedo of the earth is alpha. And we want to know the power absorbed by each square meter of the earth's surface. So I'm going to ignore the albedo for a moment, right? In which case we've done this calculation a few times, right? We have scaled down the power by using the surface area of the disk of Earth that would be intercepting the light. So that's pi r squared. Now, did they tell us? They didn't tell us the radius of the actual radius of the Earth. That ends up being fun. The denominator is the surface area of this sphere of power that leaves the sun at an Earth orbital radius from the sun. So that is 4 pi times the orbital radius squared. The orbital radius is given as d. And we were looking to average out the amount of power per unit area of the Earth. So I am going to include a term for the surface area of the sphere of Earth that has to be sharing that intercepted light, which is 4 pi r squared, right? Where r, again, is the radius of the Earth body. So if I can multiply that total power from the sun by these factors, that would give me the answer, but I then need to still incorporate the albedo. So I don't know this value, but it's fun, because I have an r squared up there, I have an r squared down here, I have a pi here, I have a pi here. So let me reduce that to p, the power, over 16 pi d squared. So I still haven't done the albedo yet, but other questions from folks about arriving at this as the power per square meter that strikes the Earth averaged out over the whole thing if our albedo was 0. I mean, it's complicated. I'm not going to lie, it's complicated. Now, in terms of what is actually absorbed, right? If the albedo is reflected, then the rest is absorbed. So the albedo is 0.3. Was that given, or did we have to know that? Oh, it just isn't alpha, right? So what's absorbed would be 1 minus alpha, all right? So I do need to multiply my numerator by 1 minus alpha, because I only want the fraction that's absorbed, not what's reflected. So that's, well, that is not answer D. And I did notice that when I did this, and I couldn't, I'm actually curious if any of you can kind of tell me if you think I made an error. I don't think I did, but D was the closest answer to what I did come up with. So can anybody that's like less geometrically challenged than me help me figure out why one of these 4s shouldn't be there, or support that I did it right and they did it wrong? Yeah, Miles.
Aren't you supposed to only do the flat?
I don't think so.
Because that would cut
Power
out
by each square meter of the Earth's surface. I mean, I could buy an argument that maybe I should just do it for half, like maybe it's implied that it's just for whoever has daytime. Because then it's going to be half, not a fourth. We're still not that answer. I really think I did it right. And the instructions do say to pick the best answer. So I'm not promising that I did it perfect and IB messed up, but they do mess up sometimes. And then their argument is, oh, well, it's still the best answer, so don't complain. I can't promise that, but I don't think I messed up. All right, anyway, we had one other page of multiple choice. That was page 7. I got one of these wrong. It wasn't the first one. So 24, I got C, and 49% of the world got that right. Anybody have follow-up questions about that? I would hope and wager that way more than 49% of you got that right. 25, I got wrong. So apparently, and I think this is fine. The answer is B. and 48% of the world got that right. I actually put C. The main reason I put C is that, yes, burning coal is very good at causing acid rain. Burning natural gas, I didn't think would be very good at causing acid rain. But what does burning natural gas produce? CO2 and water vapor. And CO2 does dissolve into water. A portion of that, what dissolves into water, forms carbonic acid. Some of that carbonic acid dissociates into the bicarbonate ion. And both of these are acids, so that does drop the pH of whatever water is absorbing the CO2. So yeah, B is fine, and that clearly is an environmental problem. Answer C, which anybody else put C? I was the only one, though. I must be the only one. The maximum efficiency is very low. Well, it's kind of true. Maybe the maximum efficiency isn't that low. I mean, it just means that we pump out more CO2 than we would have to if the efficiency was high, but maybe that then would cause an environmental problem. So whatever, I got this one wrong. A and D I thought were pretty bad answers. A, the emissions can destroy the ozone layer. That's not at all true. Chlorofluorocarbons destroy the ozone layer, and we don't emit them from fossil fuel burning. And D, the energy densities of the fuels is low compared to renewable. That's false. It's actually high compared to all of our renewables except for hydroelectric. So yeah, I picked wrong on that. 26, I said A, and 22% of people got that right. Do we want to talk about that? Okay, so 2 of you want to talk about it. So at a nuclear power station, in order to increase the chances of a chain reaction, we have a moderator built into our reactor. And the moderator slows down those high energy neutrons to put them at a speed that is way more likely to initiate a fission, right? So we're slowing down the neutrons, we are removing kinetic energy, right? We're not doing B, we're not giving kinetic energies to the neutrons, we're not making them faster. Some neutrons are absorbed, but that does not increase the chance of a fission. And then D, extra neutrons are added. No, we're using the chain reaction to produce the subsequent neutrons. Other issues with 26. Okay, and then 27 was the last one. The original, I said A, and 57% of people got that right. Anybody want to talk more about that?
Oh. I'm like answers. You're telling me what answers they do check?
They do, I just don't write that down when I'm preparing to go over stuff. What?
Did they pick one?
Oh, I don't know. I mean, I could look it up, but I didn't write it down. Alright, so then we had a single paper 2 problem, which I thought was really not that bad at all. The topic 8 paper 2 problems really run the full spectrum of ultra hard to really quite easy. And sometimes there's actually more than one topic 8 paper 2 question as well. Alright, so this one is about alternative energy supplies. I'm on page 11. The first thing we were asked to do was outline, with reference to the energy conversions in the machine, the main features of a conventional horizontal axis wind generator. That's our regular wind turbine. So this is 3 marks. I'm just going to look directly at the mark scheme here. So 1 mark is for mentioning the blades or propeller, same thing, and mentioning the turbine, generator, right? So just mentioning those 3 important parts: blades, the turbine, the generator. 1 mark is for saying that kinetic energy from the air, from the wind, does get converted into kinetic energy of the turbine. Right? I said rotational kinetic energy, but the mark scheme doesn't need to hear that. And then the 3rd mark is for saying that the rotational kinetic energy of the blades does get converted into electricity or electrical energy, and that's by the generator. Alright, it says award 1 mark maximum for an unqualified statement that kinetic energy gets converted to electrical energy. Right, it said make reference to, it says make with reference to the energy conversions in the machine, what are the main features? Alright, any follow-up issues with the first part there? Alright, number 2, we're given the mean wind speed. We need to show that the maximum power is 2 megawatts. So I did show that. Does anybody want to see my work for that? I thought this was pretty straightforward. So the equation for wind is in the data booklet. And we definitely need to use pi r squared for the amplitude. Sorry, not amplitude, for the area that the turbines are sweeping out. And then we had everything, right? We had the 45, which got put in here. We had the 1.2, which was given, and we had the 8.0 that we have to cube. So I got 1.954 times 10 to the 6th watts. In terms of those 2 marks, you got 1 mark for handling the pi r squared correctly, and then the second mark was for using it to get the 2 megawatts. Other issues with part 2. Okay. Part 3, we're told the efficiency of the generator, and we need to find how many generators this island would need to meet their energy requirements. So the first thing that I did was I took the 2 megawatts, which means that 100% of the wind kinetic energy changes to electric, and I multiplied that by the efficiency to find that really each wind turbine is producing 470 kilowatts of electricity. Amanda, if you need to get up for a second, it's fine. Questions on finding the electrical power output of a single turbine? All right, and then we were told that up at the top, we were told the islanders actually need 850 kilowatts. So I divided that 850 kilowatts by the 470 kilowatts per turbine that we could get, and I got 1.8. But I didn't just stop there. I wrote out, so they need 2 turbines. So we can't have 0.8 of a turbine. So for the 2 marks there, you got 1 mark for, you actually got 1 mark for doing that exactly, and then the second mark for figuring out that you needed 2. Other issues with page 11. Okay, page 12, we were given a graph that showed how the speed as a function of height works over land and over sea. And the first thing we were asked to do was suggest why, for every single height, the mean wind speed above the sea is greater than above land. So this is only 1 mark, and the mark scheme says you could have said that the sea is smoother, right? There's no obstacles on the sea, there's less friction, less turbulence over the sea, right? So some way of addressing that the wind isn't being interrupted, it's not having to push on as many obstacles. For part 2, you guys did pretty bad in finding the ratio of the power available from a land-based generator to the power available by a sea-based generator at a height of 60 meters. You didn't do bad at finding the speeds at a height of 60 meters. For land, the speed I found was 10 meters per second, and above the sea, I thought it was 12.4 meters per second. So that was the first thing I did. But power, wind power, is proportional to the speed cubed. So you can't just divide those 2 speeds. That's awful, right? So the ratio of the power over land to the power over sea would be 10 cubed over 12.4 cubed, which is 0.52. Right? We've seen this before. Ratios, they want decimals. Right? Don't leave it as a fraction. Other issues with page 12. Yeah, Brian.
If you said it was 12.2 over C, and you did all the math and got
Unclear to me.
comparison of it.
Unclear to me. Unclear to me, so I think that's not okay.
I'm pretty sure at 60 it is 12.2.
I'm pretty sure it's 12.4.
No.
I'm pretty sure there are 5 boxes in between 12 and 14, and 60 meters is right at the first box.
Okay, yeah.
So you would probably get, I mean, if I'm marking it, I'm going to give you 1 mark if you did everything right, but I'm not giving you both marks. Any other issues with page 12? All right, and finally we have page 13, which we've done before. Distinguish between photovoltaic cells and solar heating panels. Let me read from the mark scheme, because you already know what I think about this. 2 marks. First mark is for saying that photovoltaic cells generate electricity, or EMF. Second mark, solar panels generate thermal energy or heat. Okay. Other issues with page 13. Okay. What I would like to do is turn off the camera for a sec. I'd like you guys to dump your outer